Hello everyone, my name is Bhavesh Savare and I will be giving a presentation on dimensionality reduction. Dimensionality reduction is a key concept in machine learning because in this data world we are surrounded by high dimensional data. So there is a need for effectively using this high dimensional data. So there are only three methods that are widely used in the world that are PCA, t-SNE and UMAP. First we will see why use dimensionality reductions. Now, higher dimensional data, which is common in deep learning, presents challenges like increased computational costs, overfitting risks, and visualization difficulties known as curse of dimensionality. Imagine you are reading a book which has 1,000 pages, but it will take a lot of time. So, dimensionality reduction is like summarizing this 1,000 pages into only 10 pages, but without compromising any important data or important visualization. So dimensionality reduction projects data into a lower dimensional space, preserving important structure and variance. You can see the transition between three-dimensional space to two-dimensional and a one-dimensional space. Now, what is dimensionality reduction? So typically there are three methods for dimensionality reduction which are widely used. First is principal component analysis. Second is t-distributed stochastic neighbor embedding. And third is uniform manifold approximation and projection. So each of which balances interpretability, scalability, and preservation of data structures. Now, first we will see PCA, Principal Component Analysis. It is this method works only on linear data. It is a linear dimensionality reduction methods that finds orthogonal directions, that is principal components, which capture the maximum variance in data. That is, orthogonal direction means the direction in which all the data is stretched or shrunk. That is called the orthogonal direction and which will be considered as principal components. These principal components showcase the maximum variance between data points. It is commonly used for compression, noise reduction, and visualization. Now t-SNE. t-SNE works on non-linear data. It maps the higher dimensional data onto 2D or three-dimensional data. It preserves the local neighborhood relationships that is for a single data point, its local neighbor is all the data points surrounding in a close proximity. These are local neighborhood relationships. It is best suited for visualizing clusters, not for downstream modeling. Now is the UMAP. It is a fast, nonlinear manifold learning method. It also works on nonlinear data, but is different than t-SNE and better than t-SNE. It preserves both local and global data structure, scalable for large datasets and useful for visualization and feature extraction. Now we'll see the working of these three methods. First is the PCA. The first step is always standardizing the data, that is normalizing the features to have mean of 0 and variance of 1. Then we compute the covariance matrix. Now, covariance matrix is because we first need to find out the relationship between data points to find out the maximum variances between data points or features. This is the formula for covariance matrix. Then we calculate the eigenvalues and eigenvectors. Eigenvectors are non-zero vectors which shows the direction of the principal components. These principal components indicate on in which direction the data is stretched or shrunk, and eigenvalues are the magnitude of eigenvectors. Now, these eigenvalues and eigenvectors must satisfy this equation Ax is equals to lambda x. Here, A is the square matrix, x is the eigenvector, and lambda is the eigenvalue. Now, after finding out these eigenvectors, we sort these eigenvectors by their respective eigenvalues and select the top k components. Now we select the top k components because only the top components with higher eigenvalues can determine the most variance between data points. The more the variance between data points, the more it is easy for interpretation and visualization. Now, after selecting a top k components which has the most variance, we transform this data, that is, project this original high dimensional data onto the selected components. So this is principal component analysis. Now let's see t-SNE. So first in t-SNE, we compute pairwise distances, that is, calculate distances between each data points. Now we convert these distances to conditional probabilities reflecting neighbor likelihoods. Now we set the perplexity. Perplexity is a hyperparameter which is tuned for making this t-SNE method more adjustable and better. So perplexity is the effective number of neighbors to balance local versus global structure. Now initializing the low dimensional map, that is initialize some random points onto the low dimensional space. Now we define student t distribution. Here we are using student t distribution, not Gaussian distribution, because in Gaussian distribution, if we take data points that are far apart in high dimensional space, and if we project that data onto the low dimensional space, these data points appear very close to each other at the center. This is the problem of Gaussian distribution. But if we use student tree distribution, it has a very high end tail. So the differences between high dimensional space and low dimensional space is reduced. That is why we use student T distribution. Now we minimize the KL divergence. KL divergence is a cost function, that is a loss function, which tells us the difference between high dimensional space and low dimensional space to optimize it further. So we need to minimize this KL divergence. After minimizing the KL divergence, our data set is ready and we generate the embedding, that is visualize the clusters and neighborhoods in 2D or 3D. Now let's see UMAP, Uniform Manifold Approximation and Projection. So it is similar to t-SNE. It is slightly different. First, we construct k nearest neighbor graph. That is similar to t-SNE. We calculate the distance between each data points in the high dimensional space. Then we estimate fuzzy topological structure. That is calculate the probability, transforming the distance to probabilities. Now we initialize the low dimensional space, that is with random points on 2D or 3D. Now we optimize the layout. So for optimization, we use stochastic gradient descent to preserve both local and global structures. This step here, uh, this step here sets it apart from t-SNE and makes it faster because it also uh, preserves local and global structures. In t-SNE, t-SNE just preserves the local structures. Now we generate the embeddings, that is visualize clusters while retaining global manifold shape. The key parameter here is number of neighbors. Like in t-SNE, there was perplexity, number of neighbors defined, how many neighbors the data point should have when first calculating the distances between each data points. A small number of neighbors indicate fine local structures, and large number of neighbors define more global preservation. Now let's see the challenges and limitations. First, in PCA, the first challenge is that it only captures linear relationships. It does not work on non-linear data. Imagine if you have a data set that is in 3D and it is in spiral structure. So PCA cannot interpret the spiral structure onto a lower dimensional space. That is a limitation of PCA. Then Principal components may be hard to interpret and highly sensitive to feature scaling. Now, TSNE. TSNE's computational cost is very large for large data sets, and it is also slow. It's strongly dependent on hyperparameters such as perplexity or learning rate. It preserves local structure but falls short on preserving the global distances. Not ideal for direct feature reduction in downstream tasks. Or UMAP. UMAP is faster than t-SNE but sensitive to hyperparameters. If we mess up the hyperparameters, the visualization can be very scattered. Now, the stochastic optimization, which results may vary across runs. Risk of oversimplification if parameters aren't tuned properly. Now, let's compare these three methods. First, PCA it is best for interpretability, linear dimensionality reduction. t-SNE is best for visualizing local clusters in 2D or 3D. And UMAP is best balance of visualization plus downstream usability, scalable to large datasets. Here you can see the differences between PCA, t-SNE, and UMAP. Now, in conclusion, dimensionality reduction is essential for managing high dimensional data in machine learning or deep learning. Here, these three methods PCA, t-SNE, UMAP. PCA is fast, interpretable, linear method for pre-processing and noise reduction. t-SNE it is excellent for 2D or 3D visualization and revealing cluster structures. UMAP it is scalable, non-linear, preserves both local and global patterns, useful for visualization plus downstream tasks. And future directions are that we should create a hybrid that works on both linear plus non-linear methods and integrate neural network topics like autoencoders or virtual autoencoders.